So here class, today we will start with this definition, pseudo first order reaction. So pseudo means false, okay, and first order reaction. So such reaction whose molecularity is not 1, okay, but the order of reaction will always be 1, that is called pseudo first order reaction. Got it? Example, we can do that the hydrolysis of sucrose or hydrolysis of ester. So let me write the equation. Sucrose is, this is C12H22 O11 plus water. Got it? So this water is like, when we do this, so what will happen? It will give you C6H12O6 and C6H12O6. So here you can ask that why I am not writing 2 moles of this, because one is glucose and another is fructose. Now you'll say that both have same formula, so how the name will be different? You just learn class 11th organic chemistry. It's the same molecular formula, but the different compound is there. That means they have obviously different functional group. Got it? So that we will do in biomolecules. Don't worry about that. So here what we will do, this is sucrose. Whenever we hydrolyze this, it will give you this. So here, if we want to write the equation, rate law equation, we will write like this: C12H22O11 and water, isn't it? But listen, water concentration, pure liquid, we know that it is always 1. So finally it is R is equal to K C12H22O11, as the concentration of H2O is a constant. Got it? So here the molecularity is 1 and 1, 2. Molecularity of this reaction is 2, but the order of the reaction is 1. Got it? So that's why it is known as pseudo first order reaction. Clear? Here also hydrolysis of ester. Let's do this example. Ester, that means CS3 COO C2H5, yes, plus water. When we will hydrolyze it, we know that it is a class 10th equation, that it will give you acid and the alcohol back. Yes, got it? So again you will write this R is equal to K, and this is the concentration CS3 COO C2H5. We will not write water. Why? Because concentration of water is constant. So here also you can see that the molecularity is 2, 1 and 1, 2, but the order of the reaction is 1 only. Got it? And one more trick I'm going to give you. If any, like in the question written that A and B reacts with each other to give AB or something, C or D, whatever, and in that B is in axis. So what will be the order of reaction and what will be the molecularity of reaction? So what you will say? See, if anything, any reactant is in the axis, on that the rate of reaction doesn't depend. Just keep in your mind, if any substance, any part, any reactant or reagent is in axis, the rate of reaction doesn't depend upon that. So what will be the order of the reaction? 1 only, because it will depend only on the concentration of A, not on B, because B is in axis. Got it? But the molecularity will be 1 and 1, 2. Any doubt in this? So this is pseudo first order reaction. So the next topic is temperature dependence of the rate of reaction. How the rate of reaction depends upon temperature. So we very well know this thing. Whenever we increase the temperature, rate of reaction increases, isn't it? That we have done. If it is an endothermic reaction, it should not be exothermic reaction, or okay. So the thing is that यहाँ पे there is a relation given between the rate constant and the temperature, and that was given by Arrhenius equation. Okay, so Arrhenius says that actually experimentally it is observed that on every increase of temperature by 10 degree, that means on every 10 degree increase of temperature, the rate constant nearly becomes doubled. Somewhere you can see that the triple also, doubled or tripled likha jata hai, but whenever we do the calculation in general, it is we will consider the double only. Okay, on every 10 degree rise it will be doubled. Okay, suppose that at 273 the rate constant is K. So what will happen at 293? What will be the rate constant at 293? It will be 4K. Got it? How come? 273 it is K, so 283 it will be 2K, so 293 it will be 4K. So it increases like this, and it was given by the Arrhenius equation, and the Arrhenius equation is like this: K is equal to AE exponential, this is activation energy upon RT. This is the Arrhenius equation, where this K, we know that rate constant, A is equal to, that is Arrhenius constant, known as Arrhenius constant, and for each reaction it will, the value of this A will be given, Arrhenius constant, or it is also known as pre-exponential factor, pre-exponential factor. Okay, and EA is equal to activation energy, and R is equal to, we know that, gas constant, T is equal to temperature. Okay, but in this way we cannot solve the question, we cannot do. So there is that formula given, derived modified formula is given, we can find it. So how we will do, this is given as like this, you take log on both sides. If I will take, okay, so what it will be, log K is equal to log A E like this. Can I write? Now can I consider this is a M and this is whole N, this is M and this is N? Yes. So what it will be, log K is equal to log M plus log N. So this will be log to the exponential EA upon RT. Yes. Now this is log M power N. Can we write? This is M and this one is N. So what it will be, N log M. So can I write log A, and this minus will be here, so totally EA upon RT, and this is log to the base E. Yes, this is log K. Okay, so now log E, log to the, log exponential 1 is 1, log E value is 1. So what it will be, this is actually all this ना, it all should be the log to the base E. ये हम exponential E के form में लेंगे because it is also E ना. So we will write like this, yes, to the base E. Or ln we could have written ln instead of this ln we could have written. Okay, so this is, and now it will be, can I write like this, log to the base E K is equal to log the base A minus EA upon RT. Yes. Now we know that what, log to the base E, which is also written as ln, is equal to 2.303 log to the base 10, isn't it? And all the values can be find with this help, yes, with the help of this only. So can I replace it? So here it is, log 2.303 log to the base 10 K is equal to 2.303 log to the base 10 A minus E upon RT. Yes. Now divide both side by log by 2.303. Okay, so what you will get, this will be log to the base 10 K is equal to log to the base 10 A minus EA upon 2.303 RT, isn't it? So this is the expanded formula, expanded equation, expanded Arrhenius equation. Okay, on this basis we can solve the question. Done. So another thing also, I will explain all this activation energy later on. First, let me derive the formula. So this is if I am taking like for two different temperature, if I am taking two different temperature. Okay, So at T1, at temperature is equal to T1, the rate constant K is equal to K1. Can I write? And at T is equal to T2, the K is equal to K2. So can I write two equations for like this? So now I'm not writing to the base 10. It is quite clear that it will be log value or log to the base 10 value. Okay. So let me write log K1 is equal to this. We are performing this, we are finding this for a single equation at two different temperatures. So log A value will be constant for both, isn't it? Because it is a constant value for a particular reaction. So log, it will be A, it will remain like this, and this will be EA upon 2.303 R T1. Can I write? Similarly, this is log K2 is equal to log A minus EA upon 2.303 R T2. Can I write? Yes. Now, this is equation 1 and equation 2. So, subtract equation 2 minus equation 1. Subtract on subtracting subtracting equation 1 minus subtracting equation 1 from equation 2. So what can I write? I can write like log K2 minus log K1. Yes. And can I skip one step? This log A will be cancelled, isn't it? Equal to, this will be first. So here I will write EA minus 2.303 R T2 minus, and again minus EA upon 2.303 R T1. Can I write like this? Any problem? So now we know that log M minus log N, what it will be? Log M upon N. Can I write? Yes. And this becomes minus minus plus, isn't it? And EA upon 2.303 is common in both. So let me take it out. EA upon 2.303 let me take as a common. And what happened? 1 upon T1 minus 1 upon T2. We got the formula, isn't it? So here it is. This is the another formula. This is the relation between rate constant and temperature at two different temperatures. So derivation won't be asked. In general, derivation won't be asked, but the formula can be asked. See, if one temperature is given and log A value is given in the equation, you can use this formula and find this. And if suppose the two temperatures are given and one rate constant are given and or EA value is given, something like that, then we have to use this formula. Hope you got it. Yes. So got it. Now, if we plot a graph between L and K log to the base A, E, K कह सकते हो, and 1 upon T, then we get a graph like this. And this slope जो होता, that shows the EA upon R. Okay. Why I am taking EA upon R, not 2.303? Because I am taking L and K. If you will take it here as a log K, log to the base 10K, then you will get here 2.303 R. EA upon 2.303 R. Got it? And this is the value here, from here to here. This is ln that means frequency factor. Got it? Now the next topic is activation energy. And we all know that what is activation energy? Activation energy is the minimum energy required to convert the reactant into product. See, simply we write R change into P, but it never happens like that. R first goes to a what we say, activated complex, that excited state, and after that, if we just increase the thing nano with the nano whatever, like nanometer, nano unit, it changes to product. Got it? So this excited state, this activated part is called activated part, and the energy required to go from there to there is activation energy. Let's do with the graph. Okay. So the minimum energy required to convert the reactant into the product is known as activation energy, and it is denoted by EA like this. Okay. If we plot a graph between the potential energy and the reaction coordinate, and this is the reactant and this is the product. Okay. So it goes from this to this. This is called, and here after on this point, if we increase the things with a nano unit, it changes to the product. कुछ भी थोड़ा सा भी change करोगे, it will convert into the product. So that what we say, that complex which is formed over here, that is called activated complex, and the energy required to go the reactant from here to here is activation energy. Okay, this can be, it is not, see I have drawn the P like this, it can be here also, P यहाँ पे भी हो सकता है, it depends upon the reaction exothermic or endothermic. Okay, so what we say, which type of reaction it is, if this graph I have drawn, which type of reaction it is, like we can write this this is HR, can we write, and this is HP, isn't it? Can we write from here? H means energy, so energy for reactant is like this, here this much, and energy, and we know that delta H is equal to always P minus R. So P is lesser value, R is, so this is, that means it is going to be negative, and that means it shows it is a exothermic reaction. Khair, we don't have to go with this exothermic or endothermic, we have to just learn about this activated complex and the activation energy. Any doubt in this? Okay, so see, it is not like Maxwell said that or it is not possible that all the molecules, whatever the molecules are there, they will have the same kinetic energy at this time. It's not like that, but we will check that the most probable velocity, most probable speed, we can say kinetic energy, we can say. So most probable speed or velocity you have done in states of matter. Here we will learn about the most probable energy, kinetic energy. So if we plot a graph, like graph between the fraction of molecules over here, fraction of molecules, and next on the x-axis if we put the kinetic energy. Okay, so what we will see, we will get a graph like this, ऐसे graph आएगा, it will be like this. Got it? So we can say that at this point, this is the maximum kinetic energy, isn't it? This is the kinetic energy, and the maximum molecules are like this, this is the maximum molecules. So what the energy possessed by the maximum, if we will check here, so this much only the like what molecule will be there, isn't it? If we check this much molecule only there, if we check here this much molecule, if we check on this point, again the lesser it will be, it will go down, isn't it? So molecule will become, so kinetic energy said that it is said that the energy possessed by the maximum fraction of molecule is considered as this kinetic energy, यहाँ जो kinetic energy होगी, that will be the most probable kinetic energy. Got it? Like we do the average one, तो it is like that कि maximum बच्चों ने कितने marks obtain किए, है ना? तो that is the part. So this is the graph. Okay, now next thing we have to check that how the fraction of molecules and that kinetic energy graph is there with the T and T plus 10, यानी कि हर 10 degree increase करने पे how the graph changes, so that we will do. So as I told you that on every 10 degree increase in temperature, the rate constant becomes doubled. Okay, so if rate constant becomes double, so obviously rate of reaction will be double. Why? Because we know that R is equal to K and any reactant. Yes. So if this is rate constant is increasing, rate of reaction will also increase, isn't it? So same like that. So how it increases and how it increases and why it increases, let me explain you with the help of a graph. So if we plot a graph between fraction of molecules and kinetic energy, we get a graph like this. This is the fraction of molecules, and here we will do the kinetic energy. And as I told you about the activation energy, and I told you that the reaction will that reactant which will get this activated complex or which is having the energy with either kinetic either this activation energy or more than activation energy, then only it will convert, only it will convert into the product. Got it? If it won't get this activated complex, this activation energy, it won't convert into the product. Clear hai bache? So similarly, suppose that here I'm taking the point, and this is the point where this much energy is considered as the activation energy. So all the molecules which are either which are having this or this much energy will convert into the product. Clear? So I have plotted a graph at T temperature, somewhat T temperature. You can take it in Kelvin or degree Celsius and your wish. Okay, because if you like, you know that the relation between the Kelvin and Celsius. Okay, so you will get this. That much it shows that this much what we say, molecules are converting into the converting into the product, or you can say that the participating in the reaction. Got it? But if we plot a graph at T is equal to 10 degree. Achha, one more thing. If we increase the temperature, what will happen to the activation energy? Increase in temperature, that means the activation energy will decrease. How come? Again, you will do in this way. This formula, you can, this is the formula like this. This is a constant value. This is again, let it be like, if I'm increasing this EA, what is the relation like this? If I'm increasing the temperature, that means activation energy will decrease because it is having minus sign, isn't it? Positively sign, inversely proportional to it is. So if we are increasing the temperature, activation energy decreases, and activation energy decreases, rate constant increases. Got it? So we can say, so if we increase the temperature by 10 degree, so what a graph, like we will get a graph like this. Okay, this is the graph at T plus 10 degree. 10 degrees Celsius I'm taking through. Okay, got it? 10 degree. Okay, so what it says now, this much fraction, abhi right now it was this, this was this, yes. So earlier at T temperature, this fraction was taking part in the reaction. Now at T is equal to 10 degree, this fraction is going to, this whole fraction is going to take part in the reaction. Got it? Earlier only this was reacting. Now this also going to react. Okay, so fraction of molecule is increasing. When we increase the 10 degree temperature, fraction of molecule is increasing, and it is experimentally said that it increases by twice. The fraction of molecule increases by twice. Okay, so since fraction of molecule increases by twice on increasing 10 degree temperature, so that's why the rate of reaction, the effective collision increases, and hence the rate of reaction, rate constant increases, and hence the rate of reaction increases. So that is the reason why this every increase of 10 degree, why the rate constant becomes double. Got it? I hope it is clear. Any doubt in this? Okay, so next topic we will do that, the collision theory. That is the last topic of this chapter, and by the time okay, so for today that's it, class. Thank you, class.